Here we go. Just a second. And we're good. Okay. So hello everyone, and yeah, this is gonna be test 5 review. It's from chapter 30.1 to 30.5. And let's get going. So the first thing starts with is the induced current. So induced current is basically if you have a magnet and you have a wire, and as you push the magnet through a set of wires, you magically start seeing a current going through the circuit. So the main thing is, like, just as an advanced note, the main difference between electricity and magnetism is just the reference frame. So from a relativity point of view, electricity and magnetism, they're basically the same thing. But the difference between them is one of them looks as electricity from a really fast moving point charges like electrons, but to us it will look like magnetism, and goes the other way around. But that's not in the that's not like in your syllabus. You didn't really need to know. I just thought it would be good to know. Anyway, so yeah, any change in electric field creates a magnetic field, and any change in magnetic field creates an electric field. So yeah, so if we have a bar of magnets goes through a set of coils, it creates current in it. So basically, what happens is that the change in magnetic field of the bar is with respect to those coils. So as the magnet gets inside the coils, as like when it's outside, the magnetic field to the coils is quite weak. But as it gets inside, it keeps increasing. So it goes from low to high. So that change in magnetic field, that is what creates the current. Anyway, so yeah, there's the same thing in here. So basically what happens here, if you have a switch and you close it, what happens is that you change the electric field. Like in the beginning you had no electric field, then once you close the switch, then you start having an electric field. And that electric field in itself will create a magnetic field. So you start with no electric field. So let me write that down. So initial and midway and the final. Okay, so in the beginning, before you close the switch, this is your electric field, this is your magnetic field. So in the beginning, you had no electric field and no magnetic field. But as you close the switch, your electric field will increase. And that change in electric field in itself will make a change in your magnetic field, will make it also increase. So so in here you will have a magnetic field produced, and that magnetic field will affect this set of coils, or like this set of turns in here. So to this set of turns in here, there's a change in the magnetic field, and that change in magnetic field is what makes which induces a current in it, and that's why you will see your current meter deflects. But then when you stay, like, after you close the switch for a while, now the electric field in here is just constant. So there's no change in electric field, making no change in the magnetic field. So since there's no, again, change in magnetic field, it's not going to create any electric field in the other circuits. The same thing happens once you open. Once you open the circuit, now your electric field is decreasing. So there's a change in electric field, and that change in electric field will create in itself a magnetic field. And the magnetic field will also be changing, because as this decreasing, the electric field is increasing, the magnetic field is decreasing also. So that change in magnetic field will induce an electric field in the other set of the circuit. and that would give you a current too. Like, and we'll touch more on that, like on later sections. This is just we see what's happening, and later on we'll see why that's the case. Okay, so now we move on to motional EMF, and EMF means electromotive force. So if you have an electric field E, and inside a conducting material moving in a magnetic field B with a velocity V. So basically, if you have, let's say, like some material in here, and let's say that the magnetic field, B, which is all of this, and is into the page. Okay, and this bar of magnet, this conducting material, is moving with a velocity V. So it's just a piece of metal. It doesn't have to have any extra charge or anything. It's just a piece of metal in a magnetic field, and as it has speed inside the magnetic field, that in itself will produce an electric field inside it. And that electric field is basically that if you remember your right hand rule, if you have a moving charge in a magnetic field, it would feel force. So let me open my camera actually. And let's see here. So let's say this is your charge, or like this is your charge somehow. So if it's moving to the right and you're having a magnetic field into the page like this, so you would have, it would feel like this. Oh, this is like that. This is so weird. To the page. Yes, yeah, there we go. Okay, so yeah, let's say there's a charge in here. Okay, and it's positive. Okay, and it's moving to the right and has a magnetic field into the page, which is, yeah, have a magnetic field into the page. So it would feel a force acting on it, and this force is upwards. So what would happen is that this positive charge would go up here, and that doesn't only happen to one charge; it happens to multiple of charges. So over time, you'll start to see a buildup of positive charge in here. And if you have a buildup of positive charge in here, that means you have an opposite buildup of negative charge in the other place. So if you have positive here and negative here, that in itself will create an electric field. And the electric field will be E. So do you guys get this part? If you do get it, raise your hand. Okay, so it seems that the majority of people know really. So can anyone tell me where is the problem, or what can I go over again? Okay, let me say that really quick again. Okay, so if you have a material, let's say this is a piece of iron. Okay, it doesn't have any charge on it, just as it is. And you get it into a magnetic field, like put inside a magnetic field. And once you start moving the piece of metal, what would happen is that each point charge inside of it will feel a force, and that force will push it to the edge of the material. So what would happen is that you would have a buildup of charges on each side, and that in itself will create an electric field. So that's why if you have, yeah, forget about this sentence. This is badly worded. So yeah, if you have a conducting material moving in a magnetic field with velocity v, it would have an electric field inside it. It will experience a magnetic field inside it, and this electric field inside it is equal to the velocity multiplied by the magnetic field. Anyway, and yeah, so if you have again a buildup of charge in here and a buildup of negative charge in the other way, you can see that can be considered as a potential difference, delta V. And that delta V is just simply given with this equation. So if you have the material with a length of L, so then your potential difference would be VLB. Yeah, because if you remember that E in itself is equal to V over L, or yeah, equal to V. So that's basically what happened. If you have an electric field and the further away they get the charges from each other, there's more buildup, and so there's more potential happening, and that's basically what it is. So yeah, delta V is equal to the VLB. Okay, so yeah, let's see this and see how that applies here. So if you have a square conductor moves through a uniform magnetic field, which of the figures shows the correct charge distribution on the conductor? So the first question is, the magnetic field is pointing in or out? That's the question for you. So for the square conductor in the uniform magnetic field, so the first question you need to ask yourself, where is the magnetic field is pointing? Is it pointing into the page or out of the page? Yes, it's pointing out. Okay, so now using your right hand rule, can you figure out which charge distribution it will be in? So you have your velocity is up and your magnetic field is pointing out. So then the charge will experience a force to the right. You have your velocity up, your magnetic field out. So then it will, the charges will feel a force to the right, and this is being the force. So which one would be the right distribution? See, actually not, because the force is acting on the positive charge. So like the right hand rule only applies for the positive charge. If you want to see where the positive charge is going to be, use the right hand rule. So then we know that the force will be applied to the positive charge to the right. So then you expect the positive charges to be on the right, which means F. So here you have your positive charges. So I said F, I mean D. So D is your right answer. You can, from the first spot, from like first glance, you can rule out A and B, because if you have if you draw the magnetic field, it's gonna look like this, and that means it's parallel to the V, and that's wrong. The same thing with here, and the electric field would be pointing parallel to the V, so that's definitely wrong. So the only two options you have is C and D. So then using right hand rule, you can see where the positive charge will be, and then you can know what the distribution will be. So yeah, velocity up, the magnetic field out of the page, so the force is to the right. Okay. So now things can get a little bit more technical. So the same thing. Now, if you have a rod and has a velocity v to the right, now the electric field is into the page. So we have the velocity to the right. We have the electric field is into the page. Yeah. So the force it feels is up. So yeah, what would happen is that the positive charges will go up, and that's what it's showing. But before you would have them accumulated at the top and the negative on the bottom. But then if you put it on a conducting wire, what would happen is that those positive charges would have the freedom to go all the way around to the negative part. And that movement of all the way around, that would be current. So is that part okay? Raise your hand if that part is okay. Okay, so let's go over that again. Okay, so so far we've just been using the right hand rule. So again, if you have a metal, a bar of iron or whatever, it's neutral, doesn't have anything in it, just like normal electrons and protons, nothing special. So if it's again, so if it's in a uniform magnetic field and it's moving to the right, the charges inside the material will feel force, and you can find the direction of this force using the right hand rule. So you have the velocity to the right, you have the magnetic field is out of the page into the page, I'm sorry, and so the force will be up. So all those positive charges will feel a force pointing them, pushing them upward. Normally, if there's normally you just keep moving up and just get accumulated over here. They can't move anywhere. But then you put it on another conducting material. So now it has the freedom to go inside this material. She's going to be moving inside of it until it reaches the other side, which has a lot of negative charges in here. So if you have like a circulation of electrons or a charge, I'm sorry, that means there's a current, and that would be the same direction of the current. Someone might ask, or you might think, okay, well, why doesn't this thing in itself, this wire doesn't have any current going through it? Because it's not moving. Since this thing, this yellow thing is not moving, its V is equal to 0. So it doesn't, the charges in it doesn't feel any force. So there's nothing happening inside of it, just sitting there. That means that also the electric field inside of it is 0. So there's nothing special happening in it. Something special is happening in this bar. So as it's moving, the charges would have the freedom to start circulating around to go to the other side. And that circulation means this current. And simply, you can find that current from the previous page. So we know that V is equal to the velocity multiplied by the length multiplied by the magnitude of the magnetic field. And using, you know that V is equal to IR. So that means that I is equal to V over R. And that's basically what we've done here. V is just equal to the velocity multiplied by the length multiplied by the magnetic field. And the R is just the total resistance in this circuit, and like in this square. Okay, so I need to check because then things are gonna get a bit more confusing. Okay, so is that part okay? If that's okay, raise your hand. Okay, well that's more people. That's good. Okay, so far, what we have been saying that there's nothing special about this bar. Nothing special about it. It's just as it is, and you start moving it through the magnetic field. As you're moving it, then it would start feeling the charges in it start feeling force acting, pushing it upwards. Okay, but now let's look at the opposite thing. So if there's a current already in the material, then it will experience a force acting on it. So now let's switch it a little bit. Now let's say what we did so far. We have the magnetic field as it is. It's not changing. You move you move the bar, and from the movement you feel a force acting on it. But now, if instead you start putting a current in it, you're not moving it. You just put it there. Okay, if you just put it there, nothing is gonna happen. Just put the metal bar in there, nothing's gonna have, just sitting there as if nothing is happening. But once you put an current in it, then it will start feeling a force acting on it. So there's two cases. There's one case when you don't put any current and the current get produced by moving the metal, and the other case is when you put the current into the circuit. And once you put a current into it, the bar will start moving, either to the right or to the left. So is this part okay? Okay. Okay. So let's say there's two cases. Case number one and case two. This is one, this is two. So simply, if you move the bar, it will have a current in it. It will have an I in it, okay? But the case two, if you put a current, if you put I in the bar, the bar will move. Okay. Does that make it a little bit better? If yes, raise your hand. Okay, we got an extra one. That's better. Okay, again. So if you have your bar, once you start moving it in the magnetic field, it will produce a current. That's the case. The other case is if the bar is just sitting and you put a current into it, then it will start moving. That's just simply what it is. It just you change instead of moving it, you put a current into it, and that current will just start making it move. That's it. Anyway, so yeah, so if you have something and it starts moving, so again, so if you put a current into the wire and into the metal, it will start moving. And if anything was stationary and start moving, that means there's a force acting on it. And that force in itself will be the force from the magnetic field. Or just call it some force. It doesn't have to be. You don't really need to know what it is. It's a magnetic field. So yeah, if you have a movable wire, as in this figure, once you start moving the wire, the current will be induced. So if you have a wire and you start moving it, a current will be induced inside the wire. That current in itself will create an opposing force. So now, since you have a current in here, this current in the wire will create a force, a magnetic force. But this force will be opposing to the force you're pulling the wire with. So now, so if you want the current to be still in the wire, that means you need to apply an equal force to the opposing force, and this being the opposing force, the magnetic force. So the wire overall will be moving at a constant velocity. So here what I'm saying, basically, if like once you start moving the wire, a current will be induced in the wire. And if you have a current induced, like the system doesn't like to change. Like the wire is just sitting still and you start moving it. The system is changing and the system doesn't like to be changed. So what would happen is it will oppose you. Start like, no, I don't want to change. So so to keep it moving in a straight in a constant speed, that means you need to apply with an equal force. So if this is your force of pulling the wire, this will be the opposing force. So if you want it to be moving in a constant speed, that means your force needs to be equal to the pulling force, to the opposing force. And simply the forces will just be given with this equation. It's a bit confusing, but if anything, I would just say focus with the equations, and the equations would like there isn't really much forces happening here. So if they ask you about any force, this would be probably the equation to go to. Okay, so now the question is there any induced current in the circuit? If so, what is the direction? So if you have a bar moving to the right and you also have the magnetic field to the right, would there be any current? Yes or no? No, yes indeed, because the velocity and the electric field are pointing in the same way. So you have a velocity to the right, your magnetic field is also to the right. So there will be no force. Just it can be need to be perpendicular. So yeah, that wouldn't work. Yeah, so yeah, there will be no current. That's the long section. Anyway, so if you have a force and you have something moving with a force acting on it, that means work. And any work you can see it in terms of power. So just simply the power you put in moving this piece of wire is given by this equation. And the opposing force would also have a power equal to the same equation because it's applying the same force. So if it's applying the same force, it would have the same equation. That's simply what it is. So yeah, so from all the previous, we can see a pattern which any sort of change. Yeah, so basically what's happening here is if you have any change in the magnetic field, that will create an electric field. And any change in the electric field would also change a magnetic field. So you just have something that produces the other and just keep going and going on forever. And that's continuous changing is an important consequence of something called eddy currents. So yeah. So if you have a square loop of copper wire is pulled through a region of a magnetic field, rank in order from strongest to the weakest. The pulling forces Fa of B, of C, F, and D must be applied to keep the loop moving at a constant speed. Okay, so here before the copper loop gets into the magnetic field, is there any opposing force? Yes or no? No, yes indeed. So you can look at this as really low. Okay, so once you start getting into the magnetic field, you can start to see there's a magnetic field into the copper wire. So then you had no magnetic field, so B here is equal to 0. Now B is equal something is equal to an X. So there's a change in the magnetic field, and any change in magnetic field that will create a force. So we know that FB, so now we know for now that FB is bigger than F of A. That's for now. Okay, so now as the whole square is inside the magnetic field and it's moving inside of the magnetic field, is there any change in the magnetic field? Yes or no? No. So there isn't really much of a force you need to apply to keep it moving with the same v. So you can just say it's equal to F of A. Now you had magnetic field and you exiting. So there isn't any magnetic field. So you had a magnetic field. Let's say this is B equal to X. So in this part, you have B is equal to X. And this other part, you have B is equal to 0. So the magnetic field changed from 2x to x. So that means a change in the magnetic field, that means there's a change. So that means there's going to be an opposing force. So it's going to be harder. So since it's going to be the same change in here it changed from 0 to x, which is 1x, and here it changed from 2x to x, which is also delta change of x. So that would be f of f is equal to d. F of d is equal to f of b. So let's do a question 2. Maybe that would make things more clear, hopefully. Oh. What do you mean? There we go. Okay, yeah. So let's do question 2. Okay, so a potential difference of 0.05 volts develops across a 10 centimeter long wire as it moves through a magnetic field perpendicular to the page. What are the strength and the direction in or out of the magnetic field? So we have a block of wire. It's really bad. Okay, so it has a delta V equals 0.05 volts, and you know that this length is equal to 10 centimeter. As it moves through the magnetic field perpendicular to the page. So yeah, it also have a speed of has a V equal to 5 meters per second, and the question is, let's say this is, yeah, the question is what is B equal to? So just simply gonna use your delta equation of potential difference. So this is equal to V L B. Simply that means that B is equal to delta V over VL. think was 0.1 Tesla. Tesla is the unit of magnetic field, if I'm not mistaken. So yeah, so any question would just be easy to solve really quick if you have the equations. It would be more challenging conceptually, but it would take much more time for us to go over these. So anyway, we will then be moving on to magnetic flux. So simply, let's just say what is flux. So the purpose of this section is to get you to know what is flux, then use it to understand more about the previous sections. So flux in general is just the amount of flow of something through some area. That doesn't matter what it is. So let's say you have, I don't know, like a tap open. And there's water coming out of it. And you have some sort of a circle. So flux is simply just the amount of water coming out of this circle per second. This is simply what is flux, just the amount of water coming out through this circle in 1 second. So the flux will depend then on two things: the amount of water that's passing in 1 second, and also the area of this circle. So the smaller it gets, the smaller the flux will be, and the bigger it will. The bigger it might make it also bigger. So let's just see. So to find the flux, you need three things. You need the direction of the flow, the direction of the area, and the angle between them. So the direction of the area, that might be a little bit weird to you, but you need to be a little bit picky, because the direction of the area can give you a negative flux, if I'm not mistaken. And the angle is what defines that, what helps you. So simply, what's the use of the angle? Let's say you have light, you have a light source in here. Okay, and you have like a screen. So the light is, let's say it's perpendicular, going this way, but the screen, it's facing up that way. So that would be the angle between of them. That's the angle theta you need to know. And this angle theta is really important, because simply, if you have, let's say, this is your source of light. Let's use this as my screen. So simply, if the screen is perpendicular, like it's like, so the light is this the direction of the light. Let's see this. Let's look at this as an array of light. It's just going in a straight line. So basically, what you need is, once I put like my screen like this, is perpendicular. It is perpendicular to the array of light. So it's taking as much light rays as it can. But as I start flipping it, it takes less until it's parallel to the source. It's just going the same in the same direction. So there's barely any light touching the screen. So that's why it's important to know what is the angle. So we know once the angle is zero, you would have. So yeah, we're taking the cosine of that. So once the angle is zero, that means it's perpendicular. So this is at theta is equal to 0. But if it's lying in the same direction, that means your theta is equal to 90 degrees, because then the area is looking up and the array is going to the right. So the angle between them is 90 degrees. And cosine of 90 is 0. So that's why we take the cosine of the angle. And F is being the flow of whatever, and A is being your area. So for the magnetic flux, is denoted by this symbol, as your magnetic field multiplied by the area it's going through, and cosine the angle between them. So yeah, as I just said before, if you have your screen is pointing in the same direction, as the flow, so the angle is 0. It's really tempting to say that the screen is perpendicular. Technically, yes, the screen is perpendicular to the flow, but the direction or where the screen is pointing is in the same direction. And that's where it gets a little bit tricky. So you need the screen to be perpendicular to the flow. And for that to happen, that means the direction of the screen, so where the screen is pointing, needs to be parallel to the magnetic field. So that's simply what is happening. So yeah, if you tilt it, it would have then an angle. And as you can see, when the angle is just 0, it takes 1, 2, 3, 4 rays in it. But once it's tilted, it only takes 1 and 2. So the more you tilt it, the less flow is in it. The same thing, like once you just lie it in perpendicular, once it's pointing perpendicular to the flow, just simply nothing goes inside the flux. So just simply what you want to look is how many of those arrows goes inside your loop, and that'll be your flux. That's it. So if it lies in the same parallel to it, there's nothing goes inside the loop, just pass over it and under it. But if it's pointing in the same direction, then yes, like all the rays will go inside the loop. So yeah, just the same thing is appearing here. So let's just look at an example. If we see this, we know that then the flux is equal to BA cosine of theta, and theta here is just 0, so that's just going to equal to B of A. So what would happen if I increase the B, and the B being the magnetic field? So if I start putting double the flux that's already there, okay, this will equal to big phi, capital Phi. So now once I double the magnetic field, what would happen to phi? Yes, indeed. Yes, indeed. So yeah, because yeah, it will be double. Call this phi 1, this is phi 2. So yes, indeed, it will double. Well, then the second question would be, thought so. That's okay. What would happen if I increase the area? So let me draw that in here. Let's say this is X. Okay, so let's say that's a square. Okay, and that's the side of A. What would be your flux? And it's perpendicular. And your flux is B. As you're writing, I will do another one. Yes, will be AB. Okay, so let's call this is A, and this is 1.5 A. And it's still B. So what would your flux be? Actually, no, it's not A, it should be A squared, because it's the area. So it'd be A squared B. Yes, it would be 1.5 A squared B. Okay, so let's go a bit lower. Okay, so now this is also A, and this is also A. Now this is 2B. What would your flux be? It's actually just A squared, so it's just going to be A squared 2B. That's what would happen. So yeah, doubling the magnetic field will double the flux. But if you double the side, so now if we have this is 2A, 2A, then your flux number 4 will equal to 2A squared, wait, 2B, that will equal to 8AB squared. This should be squared. But yeah, so I said do question 4. See question 4. So what is the magnetic flux in the loop shown here? So what we have is flowing loop. Okay, and we have this is magnetic field in, and this is out. This is equal to 2t. This is equal to 1t. Oh, this looks like an I. This is a t. And this is 20 centimeters. This is 20 centimeters. And that is another 20 centimeters. So what is the total flux equal to? Is equal to what? How can we find that? Yes, yes, indeed. So we'll call this part from the flux in this one. Call it 1, and this part call it flux 2. This is flux 2. So flux 1 is just say it's equal to flux 1 plus flux 2. So flux 1 is equal to what? Is equal to 2t multiplied by 0.2 squared, and that equal to 0.8. Okay. What about this one? Close, but not exactly. We have this into the page, but have the other one is out of the page. So the magnetic field in is opposite to the out. So whatever is going in, there's something else coming out. So it should be negative. Yes, indeed. So this one is going to be negative t 0.2 squared. That will equal to 0.04 negative. So those two combined, so the total flux is equal to 0.04. This is one way to do it. Another way to do it, I just need to check for something. 0.02 squared. Yes, indeed. Okay, so yeah, this is one way to do it. The other way is to do it is what you can do is you can see what is the total magnetic field inside. So you know the total magnetic field have 2 plus and 1 minus. So the total B total is just going to equal to 2t minus 1t is equal to 1 Tesla. And you can take that and just multiply it by the overall area. So the total flux, yeah, is equal to 1 multiplied by 0.2 multiplied by 0.2 plus 0.2, which is equal to 1 multiplied by 0.2 multiplied by 0.4. Something missing. No, yeah, yes, no. 0.8. Oh my goodness. This is, I'm so dumb. I'm sorry. Okay, so 2 multiply 0.2 squared. Yeah, that's 0.8. If this is 1, this is like that. This should be 8. And this should be 4. Doing something wrong here. Because it should give the same answer. Okay, this gave us 4. there anything wrong with my calculations? Does anyone know? Something is missing. Yes, you can't add flux. I'm sorry. Yes, you can't add flux. Now I remember. Yeah, you can't add flux. Flux is something that doesn't get added. Yeah, flux does not get added. So yeah, scrap this. This is wrong. Yeah, this is wrong. This is wrong. You don't add flux. This is totally wrong. You don't add flux. You add the magnetic field though. Yes. Okay, well, I'm glad I did this. Yeah, you don't add flux. You do add the magnetic field. So what you do is you find the total magnetic field inside, then you multiply by the area. Sorry about that. Flux does not get added. Magnetic field does. So the overall magnetic field inside is just only 1 Tesla. You have 2 in and 1 out. You have 2 in and 1 out. So they cancel each other, and you only have in total 1 in. So that 1 in goes through this full area. And this is how you find your flux. Okay, is that part okay? Please raise your hand if that's part okay. Okay. So yeah, just to say once more, to find the flux is you add all the magnetic field and then multiply by the area. You don't add flux, you add the magnetic field. Okay. Okay, so then we jump to Lenz's law. So basically what it says, if there's an induced current in a closed conducting loop, if and only if the magnetic flux through the loop is changing. The direction of the induced current is such that the induced magnetic field opposes the change in flux. So it's just simply the same thing we've been doing over and over again. So if you look here in this example, what happens is this is an area, and here there's a magnetic field. So as you get into the magnetic field, the flux is changing. You had in the beginning no magnetic field, then you start to have a magnetic field. So the flux is changing. And that change in flux induces a current into the wire, into the copper wire. And that current into the wire, its whole purpose is just to opposes the change that's happening, which is the magnetic field. So now if you have the magnetic field is pointing out, so there's a current get induced inside the copper wire to make producing a magnetic field pointing in, just to opposes this, excuse me, this out change of magnetic field. So that's basically what Lenz's law says. So again, so there is an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing. So as the magnetic flux gets changed in the loop, so if the loop doesn't have any magnetic field, now it does, then there will be an induced current. And that induced current will be in a direction just to oppose the change in flux. So simply, if you have a wire, the magnetic field is not changing or anything. So it's just sitting there, nothing is happening. So the magnetic field is as it is. So there would be no current and there would be no magnetic field happening. But if the magnetic field start to increase, the system doesn't like that. The system doesn't like change. It wants to be in its original state. So what it will do is will create a magnetic field in the opposite direction. If the magnetic field is increasing up, then it will make a magnetic field points down just to cancel it, to cancel that change. And to have that magnetic field in the first place, you need current. So what happens is as you change the magnetic field, there will be a current get induced. And that induced current would just produce a magnetic field in the opposite direction, and that's why you feel a force. And basically what I've been doing in the previous sections is we getting to know why there's a current in the first place. Like you might ask, okay, if the magnetic field is increasing, why there's induced current? And that induced current is because there's a force it happens inside of the charges inside the wire, makes it go to spin, makes it move, and that movement creates a current. And that current points in the opposite direction of the current of the magnetic field. So just simply, if you have a change of magnetic field in one way, the system will make a magnetic field in the opposite way, just simply as it is. So if now you have the magnetic field is decreasing, so then the system doesn't like that. It will make a magnetic field in the opposite direction. So if it's increasing, that means it's getting lower. So it will just make a magnetic field in the opposite direction. Same thing, if you have here, the magnetic field now is pointing the other way. There's no change in the magnetic field, so there's no change in the flux. So there's no current, there's nothing is happening. Everything is peaceful. But once you start increasing the magnetic field, the system will make a magnetic field pointing in the opposite direction. And that magnetic field in the opposite direction happens because there's a current inside the wire. Same things happens here. If the magnetic field is decreasing, the system doesn't like that. So I will try to do something to oppose that change. And you can simply know the direction of the magnetic of the current using your right-hand rule. So in this case, you want the magnetic field to point down. So you want your magnetic field to point down. That means your current will be in this direction. And since it's a loop, it's going to be going counterclockwise. And that's what we have in here. The same thing in the other way. If you want magnetic field to point up, so that means your current is to the right. And just as you go around the loop, they'll be counterclockwise. So here, if we have a current carrying wire is pulled away from a conducting loop in a direction shown, as the wire is moving, is there a CW counterclockwise currents or counterclockwise or no current? So simply, if you just draw the magnetic field around this wire, it would be so intense around it, but as we go further, it just decreases. So it would also be a magnetic field in here. So as you moving the wire away from this loop, when it was so close, the magnetic field was intense. But as you're pulling it away, the magnetic field keeps decreasing. So that means there will be change in the magnetic field. And if there's a change in the magnetic field in a certain area, that means there's a change in the flux. So that means since there's a change in the flux, that means there will be a current. So now we know the option for no current, that's wrong. That's false. There has to be a current inside of the loop. Okay, so is this part okay? If it is, raise your hand. Okay, say that again. Okay. For a wire, the magnetic field close to the wire is really intense. And the further you go from the wire, let's say this is our loop. And the close you are to the wire, it's really intense. The further away you go from the wire, the magnetic field decreases. And that's using an equation for the magnetic field produced by a wire. I don't remember what it is, but if you looked at it, it's not constant everywhere. So the further you get away from the wire, the less magnetic field you will feel. So if the wire in the beginning was so close to the loop, as it is getting further away, the magnetic field the loop is experiencing is decreasing. So there's a change in the magnetic field for the loop. And if there's a change in the magnetic field, that means there's a change in the flux. The flux used to be really high, but now it's decreasing. So So now, yeah, so now it's decreasing. So there's a change in the flux. Any change in the flux, that means that the system doesn't like that. It wants to reproduce magnetic field in the other way. So that means there will be a current in the wire, and that's why there has to be a current in the wire. Now the question is, what would be the current? So the first question is, we need to find the direction of the first of the magnetic field produced by the wire. So the wire is going to the current is going to the left. That means the magnetic field is pointing into the page. Magnetic field is pointing inside the page. So it's going inside of the loop. So if the magnetic field is decreasing, that means that the wire, that means there's a magnetic field into the loop. Okay, so from the wire, we know the magnetic field is going to be pointing into the page. As it is decreasing, so if you just checked in here, if it's going inside of the loop and it is decreasing, that means the magnetic field induced will be also in the same direction. So that means the magnetic field the current wants to produce is also into the page. And if it's into the page, that means the current has to be here to the left, and here up, and here to the right. That's being the current, which means counter clockwise. So CW. That would be the answer. I'm going much over the time, so I'll just skim through these. Okay, Faraday's law, just simply saying the change of flux over time is potential, as the EMF. So which you can just look at it as delta V. So any change in the magnetic flux over time divided by the time, that will be your potential difference. That's simply what it is. And using this fact, with playing a little bit with the equations, you will get the exact same results we got before. Just simply what it is saying. So here, if you have a conducting loop is halfway into the magnetic field, and suppose the magnetic field begins to increase rapidly in strength, what would happen to the loop? Okay, so now the magnetic field is into the page and it's increasing. It's increasing rapidly into the page. The system doesn't like that. So what it will do is will produce a magnetic field opposite to the system. So that means that this loop will start producing magnetic field out of the page. And if it is pointing out of the page, that means that when you curl your finger, it needs to point out of the page. So the current is pointing to the right. So now that means that the current is going to the right. It's going counterclockwise. Okay, so now here where it gets tricky. A little bit, maybe, we'll see. Okay, so now you have the magnetic field is pointing out and you have your current is to the right. So using the right hand rule, the magnetic field, the current is pointing to the right, magnetic field is pointing out. That means in this part, this is to the right and this is out of the page. So that means there's a force will be acting downwards. So in this part, there will be a force acting downwards. As we have the I over here, the current will be going this way. So now we have the current is pointing to the left, magnetic field is out of the page, and the force is pointing up. So now we have another force is pointing up. Now let's look at those two sides. This side doesn't have a magnetic field in it, so we can just ignore anything acting on it. So the only thing remaining is this part. Here we have the magnetic field, the current is pointing down, and the magnetic field is pointing out. So that means that the force is to the left. So simply, overall, we have a force to the left. So the lobe will be pulled to the left, and the magnetic field will be out. Do you have that fact? No, we don't. I said it would be out of the page. It will be pulled to the left into pushed upwards toward the top of the page. No. It's pushed downwards toward the bottom of the page. No. Be pushed to the left. Yes. Into the magnetic field. This means points in, that means points out. Goes to the left. Okay, this is wrong. So yeah, it just goes to the left, and the magnetic field points out. But yeah, that's just simply what it is. I'm much over time. Stop recording here. If you have any questions, please let me know.